Okay, this is it. This is then the second lecture in linear algebra, and I've put below my main topics for today. That I put right there a system of equations that's going to be our example to work with. But what are we going to do with it? We're going to solve it. And the method of solution will not be determinants. Determinants are something that will come later. The method we'll use is called elimination. And it's the way every software package solves equations. And so, and elimination, well, if it succeeds, it gets the answer. And normally it does succeed. If the matrix A that's coming into that system is a good matrix, and I think this one is, then elimination will work. We'll get the answer in an efficient way. But why don't we, as long as we're sort of seeing how elimination works, it's always good to ask, how could it fail? So at the same time, we'll see how elimination decides whether the matrix is a good one or has problems. Then, to complete the answer, there's an obvious step of back substitution. In fact, the idea of elimination is, you would have thought of it, right? I mean, Gauss thought of it before we did, but only because he was born earlier. It's a natural idea. And died earlier, too. Okay, so, but then, and you've seen the idea. But now, the part that I want to show you is elimination expressed in matrix language, because the whole course, all the key ideas get expressed as matrix operations, not as words. And one of the operations, of course, that we'll meet is how do we multiply matrices and why. Okay, so there's a system of equations. 3 equations in 3 unknowns. And there's the matrix, the 3 by 3 matrix. So this is the system AX equal B, you could say. This is our system to solve. AX equal, and the right-hand side is that vector 2, 12, 2. Okay. Now, when I describe elimination, it gets to be a pain to keep writing the equal signs and the pluses and so on. It's that matrix that totally matters. Everything is in that matrix, but behind it is those equations. So what does elimination do? What's the first step of elimination? We accept the first equation, it's okay. I'm going to multiply that equation by the right number, the right multiplier, and I'm going to subtract it from the second equation. With what purpose? So what that will decide what the multiplier should be. Our purpose is to knock out the x part of equation 2. So our purpose is to eliminate x. So what do I multiply? And again, I'll do it with this matrix because I can do it short. What's the multiplier here? What do I multiply? Equation 1 and subtract. Notice I'm saying that word subtract. I'd like to stick to that convention. I'll do a subtraction. So first of all, this is the key number, right, that I'm starting with. And that's called the pivot. I'll put a box around it and write its name down. That's the first pivot. The first pivot. Okay, so I'm going to use, that's sort of like the key number in that equation. And now what's the multiplier? So I'm going to, my first row won't change, but that's the pivot row. But I'm going to use it, and now finally let me ask you what the multiplier is. Yes? 3. 3 times that first equation will knock out that 3. Okay, so what will it leave? So the multiplier is 3. 3 times that will make that 0. That was our purpose. 3 2s away from the 8 will leave a 2. and 3 ones away from 1 will leave a minus 2. And this guy didn't change. Okay. Now the next step, so that step of, this is forward elimination, and that step's completed. Oh, well, you could say, wait a minute, what about the right-hand side? Shall I carry, the right-hand side is like, gets carried along. Actually, MATLAB finishes up with the left side before, and then just goes back to do the right side. Maybe I'll be MATLAB for a moment and do that. Okay, so I just, like, I'm leaving a room for a column of B, the right-hand side, but I'll fill it in later. Okay, now the next step of elimination is what? Well, strictly speaking, I cleaned up, this position that I cleaned up was like the 2, 1 position, row 2, column 1. So I got a 0 in the 2, 1 position. I'll use 2, 1 as the index of that step. The next step should be to finish the column and get a 0 in that position. So the next step is really the 3, 1 step, row 3, column 1. But of course, I already have 0. Okay, so the multiplier is 0. I take 0 of this equation away from this one, and I'm all set. So I won't repeat that, but there was a step there which MATLAB would have to look. It would look at this number and do that step unless you told it in advance that it was 0. Okay, now what? Now we can see the second pivot, which is what? The second pivot, see, we've eliminated, x is now gone from this equation, right? We're down to 2 equations in y and z. And so now I just do it again. Like, everything's recursive at this. This is such a basic algorithm, and you've seen it. But carry me through one last step. So this is still the first pivot. Now the second pivot is this guy who has appeared there. And what's the multiplier, the appropriate multiplier now? And what's my purpose? Is to clean up, is to wipe out the 3, 2 position, right? This was the 2, 1 step. And now I'm going to take the 3, 2 step. So this all stays the same. 1, 2, 1, 0, 2, minus 1. And the pivots are there. Now I'm using this pivot. So what's the multiplier? 2. 2 times this equation, this row, gets subtracted from this row and makes that a 0. So it's 0, 0, and is it a 5? Yeah, I guess it's a 5. Is that right? Because I have a 1 there, and I'm subtracting twice this, so I think it sits a 5 there. There's the third pivot. So let me put a box around all 3 pivots. Is there a, I think that, did I just invent a -1? I'm sorry that the tape can't correct that as easily as I can. Okay, is that, thank you very much. You get an A in the course now. Is that correct? Is it correct now? Okay. So the 3 pivots are there. I know right away a lot about this matrix. This elimination step from A, this matrix I'm going to call U. U for upper triangular. So the whole purpose of elimination was to get from A to U. And literally, that's the most common calculation in scientific computing. And people think of, how could I do that faster? Because it's a major, major thing. But we're doing it the straightforward way. We found 3 pivots. And by the way, I didn't say this. Pivots can't be 0. I don't accept 0 as a pivot. And I didn't get 0. So this matrix is great. It gave me 3 pivots. I didn't have to do anything special. I just followed the rules. And And the pivots are 1, 2, and 5. By the way, just because I always anticipate stuff from a later day, if I wanted to know the determinant of this matrix, which I never do want to know, but I would just multiply the pivots. The determinant is 10. So even things like the determinant are here. Okay. Now, let me talk about failure for a moment, and then come back to success. How could this have failed? How could, by fail I mean fail to come up with 3 pivots? Tell me, I mean, there are a couple of points. I would have already been in trouble if this very first number here was 0. If it was a 0 there, suppose that had been a 0. There were no x's in that first equation. Does that mean I can't solve the problem? Does that mean I quit? No. What do? I switch rows. I exchange rows. So in case of a 0, I will not say 0 pivot. I will never be heard to utter those words, 0 pivot. But if there's a 0 in the pivot position, maybe I can say that, I would try to exchange for a lower equation and get a proper pivot up there. Okay, now, for example, this second pivot came out 2. Could it have come out 0? Actually, if I changed that 8 a little bit, I would have got, again, a little trouble. What should I change that 8 to so that I run into trouble? A 6. If that had been a 6, then this would have been 0, and I couldn't have used that as the pivot, but I could have exchanged again. In this case, because when can I get out of trouble? I can get out of trouble if there's a non-zero below this troublesome 0. And there is here, so I would be okay in this case. If this was a 6, I would survive by a row exchange. Now, of course, it might have happened that I couldn't do the row, that there was zeros below it, but here there wasn't. Now, I could also have got in trouble if this number 1 was a little different. See, that 1 became a 5, I guess, by the end. So can you see what number there would have got me trouble that I really couldn't get out of? Trouble that I couldn't get out of would mean if the pivot is, if 0 is in the pivot position and I've got no place to exchange. So there must be some number which if I had here, it would have meant failure. -4, good. If it was a -4 here, if it happened to be a -4, I'll temporarily put it up here. If this had been a -4z, then I would have gone through the same steps. This would have been a -4. It still would have been a -4. But at the last minute, it would have become 0. And there wouldn't have been a third pivot. The matrix would have not been invertible. Well, of course, the inverse of a matrix is coming next week, but you've heard these words before. So that's how we identify failure. There's temporary failure when we can do a row exchange and get out of it, or there's complete failure when we get a 0 and there's nothing below that we can use. Okay. Let's stay with back to success now. In fact, I guess the next topic is back substitution. So what's back substitution? Well, now I better bring the right-hand side in. So what would MATLAB do, and what should we do? Let me bring in the right-hand side as an extra column. So there comes B. So it's 2, 12, 2. This is, I would call this the augmented matrix. Augment means you've tacked something on. I've tacked on this extra column. Because when I'm working with equations, I do the same thing to both sides. So at this step, I subtracted 2 of the first equation away from the second equation so that this augmented, I even brought some colored chalk, but I don't know if it shows up. So this is like the augmented. No, damn, circled the wrong thing. Okay, here is B. Okay, that's the extra column. Okay, so what happened to that extra column, the right-hand side of the equations, when I did the first step? So that was 3 of this away from this. So it took, the 2 stayed the same, but 3 2's got taken away from 12, leaving 6, and that 2 stayed the same. So this is how it's looking halfway along. And let me just carry to the end. The 2 and the 6 stay the same, but what do I have here? Oh gosh. Help me out now. What? So now this is still like forward elimination. I got to this point, which I think is right. And now what did I do at this step? I multiplied that pivot by 2, or that whole equation by 2, and subtracted from that. So I think I take 2 6s, which is 12, away from the 2. Do you think minus 10 is my final right-hand side? The right-hand side that goes with u, and let me call that once and forever the vector c. So c is what happens to b, and u is what happens to a. Okay, there you've seen elimination clean. Okay. Oh, what's back substitution? So what are my final equations then? Can I copy these equations? X plus 2y plus z equals 2 is still there. Then 2y minus 2z equals 6 is there. And 5z is minus 10. Okay. Those are the equations that these numbers are telling me about. Those are the equations u, x equals c. Okay, how do I solve them? What one do I solve for first? Z. I see immediately that the correct value of z is -2. And what do I do next? I go back upwards. I now know z here. So if z is -2, that's 4 there. Is that right? And so 2y plus the 4 is 6. Maybe y is 1. This is back substitution. We're doing it on the fly because it's so easy. And then x is, so x, 2y's is 2 minus 2. Maybe x is 2. So you see what back substitution is. It's the simple step solving the equations in reverse order because the system is triangular. Okay, good. So that's elimination and back substitution, and I kept the right-hand side along. Okay, now so that like is first piece of the lecture. What's the second piece? Matrices are going to get in. So I wrote stuff with x, y's, and z's in there. Then I really got the right shorthand, just writing the matrix entries. And now I want to write the operations that I did in matrices, right? I've carried the matrices along, but I haven't said the operation, those elimination steps, I now want to express as matrices. Okay, here they come. So now this is elimination matrices. Okay, let me take that first step which took me from 121, 381, 041. I want to operate on that. I want to do elimination on that. Okay. Okay. Now, actually, I'm remembering a point I want to single out as especially important. Let me move the board up for that. Because when we do matrix operations, we got to be able to see the big picture. Okay, last time I spoke about the big picture of when I multiply a matrix by a right-hand side. If I have some matrix there and I multiply it by 3, 4, 5, let's say, so here's a matrix. What did I say? Well, I guess I only said it on the videotape, but do you remember how I look at that matrix multiplication? The result of multiplying a matrix by some vector is a combination of the columns of the matrix. It's 3 times the first column. It's 3 times column 1 plus 4 times column 2 plus 5 times column 3. Okay, I'm going to come back to that multiple times. What I wanted to do now was to emphasize the parallel thing with rows. Why? Because all our operations here for this, like this 2 weeks of the course, are row operations. So I have to, this isn't what I need for row operations. Let me do a row operation. Suppose I have my matrix, again, and suppose I multiply on the left by some, let's say, 1, 2, 7. Again, I'm just saying what the result is. And then we'll say how matrix multiplication works, and we'll see that it's true. Okay. But maybe already I'm making, I'm sort of bringing up the central idea of linear algebra, is how these matrices work by rows as well as by columns. Okay, how does it work by rows? So this is that's a row vector. I could say that's a 1 by 3 matrix, a row vector multiplying a 3 by 3 matrix. What's the output? What's the product of a row times a matrix? And okay, it's a row. A column. A matrix times a column is a column. So matrix times matrix times a column is a column. And we know what column it is. Over here, I'm doing a row times a matrix, and what's the answer? It's 1 of that first row, so it's 1 times row 1 plus 2 times row 2 plus 7 times row 3. As we do matrix multiplication, keep your eye on what it's doing with whole vectors. And what it's doing in this case is it's combining the rows. We have a linear combination of the rows. Okay, I want to use that. Okay, now, so my question is, what's the matrix that does this first step? That subtracts 3 of equation 1 from equation 2. That's what I want to do. So this is going to be a matrix that's going to subtract 3 times row 1 from row 2. And leaves the other rows the same. The answer is going to be that. So whatever matrix this is, and you're going to tell me what matrix will do it, it's the matrix that leaves the first row unchanged, leaves the last row unchanged, but takes 3 of these away from this, so it puts a 0 there, a 2 there, and a -2. Good. What matrix will do it? It's these. It should be a pretty simple matrix because we're doing a very simple step. We're just doing this step that changes row 2. So actually, row 1 is not changing. So tell me how the matrix should begin. 1. So the first row of the matrix will be 1, 0, 0. Because that's just the right thing. That takes 1 of that row and none of the other rows, and that's what we want. What's the last row of the matrix? 0, 0, 1. Because that takes 1 of the third row and none of the other rows. That's great. Okay. Now, suppose I didn't want to do anything at all. Suppose my row, well, I guess maybe I had a case here when I already had a 0 and didn't have to do anything. What matrix does nothing? Like just leaves you where you were. If I put in 0, 1, 0, that's the matrix. What's the name of that matrix? The identity matrix, right. So it does absolutely nothing. It just multiplies everything and leaves it where it is. It's like a 1, like the number 1 for matrices. But that's not what we want, because we want to change this row 2. So what's the correct? What should I put in here now to come out to do it right? I want to get, what do I want? What am I'm after? I want to subtract I want 3 of row 1 to get subtracted off. So what's that row? What's the right matrix to finish that matrix for me? -3 goes here. And what goes here? That 1. And what goes here? The 0. That's the good matrix. That's the matrix that takes -3 of row 1 plus the row 2 and gives the new row 2. Should we just check some particular entry? How do I check a particular entry of a matrix in matrix multiplication? Like suppose I wanted to check the entry here that's in row 2, column 3. So where does the entry in row 2, column 3 come from? I would look at row 2 of this guy and column 3 of this one to get that number. That number comes from the second row and the third column, and I just take this dot product, -3, I'm multiplying, -3 plus 1, and 0 gives the -2. Yeah, it works. So we got various ways to multiply matrices now. We're sort of informally. We've got by columns, we will have by columns, by rows, by each entry at a time. But it's good to see that matrix multiplication when one of the matrices is so simple. So this guy is our elementary matrix. Let's call it E for elementary or elimination. And let me put the indexes 2, 1, because it's the matrix that we needed to fix the 2, 1 position. It's the matrix that we needed to get this 2, 1 position to be 0. Okay, good enough. So what do I do next? I need another matrix, right? I need to, there's another step here, and I want to express the whole elimination process in matrix language. So tell me what now, so next step, step 2, which was what? Subtract what was the actual step that we did? I think I subtracted, do you remember? I had a 2 in the pivot and a 4 below it, so I subtracted 2 times row 2 from row 3. From row 3. Tell me the matrix that'll do that. And tell me its name. Okay, it's going to be E for elementary or elimination matrix. And what's the index number that I use to tell me what E32, right? Because it's fixing this 3, 2 position. And what is the matrix now? Okay, you remember, so E32 is supposed to multiply my guy that I have, and it's supposed to produce the right result, which was it's supposed to leave the first row, it's supposed to leave the second row, and it's supposed to straighten out the third row to this. And what's the matrix that does that? 1, 0, 0, right? Because we don't change the first row. And the next row we don't change either. And the last row is the one we do change. And what do I do? Let's see, I subtract 2 times, so what's this row? What's this here? 0, right? Because the first row is not involved. The second, it's just in the 3, 2 position, isn't it? The key number is this minus the multiplier that goes sitting there in that 3, 2 position. So is it a minus 2 to subtract 2, and then this is a 1, so that the overall effect is to take minus 2 of this row plus 1 of that. Okay. So I've now given you the pieces. The elimination matrices, the elementary matrices that take each step. So now what? Now the next point in the lecture is to put those steps together into a matrix that does it all and see how it all happens. So now I'm going to express everything we did today so far on A. Was to start with A, we multiplied it by E21, that was the first step, and then we multiplied that result by E32, and that led us to this thing, and what was that matrix? U. You see why I like matrix notation, because they're in like little space, a few bits when it's compressed on the web, is this whole lecture. Okay. Now, there are important facts about matrix multiplication. And we're close to maybe the most important. And that is this. Suppose I ask you this question. Suppose I start with a matrix A, and I want to end with a matrix U, and I want to say, what matrix does the whole job? What matrix takes me from A to U, using the letters I've got? So, and the answer is simple. I'm not asking but it's highly important. How would I create the matrix that does the whole job at once, that does all of elimination in one shot? It would be, I would just put these together, right? In other words, this is the thing I'm struggling to say. I can move those parentheses. If I keep the matrices in order, I can't mess around with the order of the matrices. But I can change the order that I do the multiplications. I can multiply these two first. In other words, you see what those parentheses are doing? It's saying multiply the e's first, and that gives you the matrix that does everything at once. Okay. So this fact that this is automatically the same as this, for every matrix multiplication, which I'm conscious of still not telling you in every detail, but like you're seeing how it works. And this is highly important, and maybe tell me the long word that describes this law for matrices, that you can move the parentheses. It's called the associative law. I think you can now forget that. But don't forget the law. I mean, like forget the word associative. I don't know. But don't forget the law. Because actually, we'll see so many steps in linear algebra, so many proofs even of main facts come from just moving the parentheses. It's and it's not that easy to, I mean, to prove that this is correct, you have to go into the gory details of matrix multiplication, do it both ways, and see that you come out the same. Maybe I'll leave the author to do that. Okay, so there we go. That's how so there's a single matrix. I could call it E. Now, while we're talking about these matrices, tell me there's another type of elementary matrix, and we already said why we might need it. We didn't need it in this case, but it's the matrix that exchanges two rows. It's called a permutation matrix. Can you just tell me what that would be? So I'm just this is a slight digression. And so let me figure out where I'm going to put a permutation matrix. You'll see I'm always squeezing stuff in. So permutation. Or in fact, this one exchange rows. Shall I exchange rows 1 and 2 just to make life easy? So if I had my matrix, let me just do 2 by 2, A, B, C, D. Suppose I want to find the matrix that exchanges those rows. What is it? So the matrix that exchanges those rows, the row I want is CD, and it's there. So I better take one of it. And the row I want here is up top, so I'll take one of that. So actually, the easy way, this is my matrix that I'll call P for permutation. It's the matrix, actually the easy way to find it is just do the thing to the identity matrix, exchange the rows of the identity matrix, and then that's the matrix that'll do row exchanges for you. Suppose I wanted to exchange columns instead. Columns have hardly got into today's lecture, but they certainly are going to be around. How could I, if I started with this matrix A, B, C, D, then I wouldn't, I'm not even going to write this down. I'm just going to ask you. Because in elimination, we're doing rows. But suppose we wanted to exchange the columns of a matrix. How would I do that? What matrix multiplication would do that job? Actually, why not? I'll write it down. So this is I'll write it under here and then hide it again. Okay, suppose I had my matrix A, B, C, D, and I want to get to AC over here and BD here. What matrix does that job? Can I cook up some matrix that produces that answer. And you can see from where I put my hand, I was really asking, can I put a matrix here on the left that will exchange columns? And the answer is no. So I'm just bringing out again this point that when I multiply on the left, I'm doing row operations. So if I want to do a column operation, where do I put that permutation matrix? On the right. If I put it here, where I just barely left room for it, so I'll exchange the two columns of the identity, then it comes out right. Because now I'm multiplying a column at a time. This is the first column, and says take none of that column, one of this one, and then you got it. Over here, take one of this one, none of this one, and you've got AC. So, in short, to do column operations, the matrix multiplies on the right. To do row operations, it multiplies on the left. Okay. Okay. And it's row operations that we're really doing. Okay. And of course, I mentioned in passing, but I better say it very clearly, that you can't exchange the orders of matrices. And that's just the point I was making again here. A times B is not the same as B times A. You have to keep these matrices in their Gauss-given order here, right? But you can move the parentheses. So that, in other words, the commutative law, which would allow you to take it in the other order, is false. So we have to keep it in that order. Okay. So what next? I could do this multiplication. I could do E32. So let me come back to see what that was. Here was E21. And here is E32. And if I multiply those matrices together, E32 and then E21, I'll get a single matrix that does elimination. I don't want to do it that. I don't. If I do that multiplication, there's a better way to do this. And so in this last few minutes of today's lecture, can I anticipate that better way? The better way is to think not how do I get from A to U, but how do I get from U back to A? So reversing steps is going to come in. Inverse, I'll use the word inverse here. Okay, so let me make the first step at what's the inverse matrix. All the matrices you've seen on this board have inverses. I didn't write any bad matrices down. We spoke about possible failure, and for a moment we put in a matrix that would fail. But right now, all these matrices are good. They're all invertible. And let's take the inverse. Well, let me say first, what does the inverse mean, and find it. Okay, so we're getting a little leg up on inverses. Okay, so this is the final moments of today. Sorry, he's still there. Okay, inverses. Okay, and I'm just going to take one example and then we're done. The example I'll take will be that E. So my matrix is 1, 0, 0, minus 3, 1, 0, 0, 0, 1. And I want to find the matrix that undoes that step. So what was that step? The step was subtract 3 times row 1 from row 2. So what matrix will get me back? What matrix will bring back, you know, if I started with a 2, 12, 2 and it changed it to a 2, 6, 2 because of this guy, I want to get back to the 2, 12, 2. I want to find the matrix which undoes elimination, the matrix which multiplies this to give the identity. And you can tell me what I should do in words first, and then we'll write down the matrix that does it. If this step subtracted 3 times row 1 from row 2, what's the inverse step? I add 3 times row 1 to row 2, right? I add it back. What I subtracted away, I add back. So the inverse matrix in this case is, I now want to add 3 times row 1 to row 2. So I won't change row 1, I won't change row 3, and I'll add 3 times row 1 to row 2. That's a case where the inverse is clear. It's clear in words what to do. Because what this did was simple to express. It just changed row 2 by subtracting 3 of row 1. So to invert it, I go that way. And if we do that calculation, 3 times this row plus 1 times this row comes out the right row of the identity. Okay, so inverses are, and so if this matrix was E, and this matrix is I for identity, then what's the notation for this guy? E to the minus 1, E inverse. Okay, let's stop there for today. That's a little jump on what's coming on Monday. So, see you Monday.